All right, welcome everyone. Let's get right into it. This is your rapid-fire review session on the absolute must-know concepts for operating systems. If you've got an exam breathing down your neck, well, you're in exactly the right place.
Look, the goal today is simple. We're aiming for clarity. We're going to take all those jumbled concepts and turn them into pure confidence so you can walk into that exam and just absolutely crush it. This is your Core Concepts Study Guide. Let's do this.
So here's our game plan. We're going to start with the absolute bedrock, the four components, and from there, we'll build our way up to the more complex systems. Think of each of these topics as a key piece of a giant puzzle.
Okay, first things first. We have to talk about the fundamental structure of any computer system. Seriously, if you get these layers, everything else the OS does just clicks into place, because it's all about managing how they all talk to each other. Think of it like a stack. Right at the bottom, you've got the physical hardware. The operating system sits right on top of that, kind of like a manager. Then you have the application programs we all use every day. And finally, sitting at the very top of it all, that's us, the users.
Let's just break that down a little. So the hardware, that's your CPU, your memory, your input/output devices like your keyboard or monitor, that's the raw power, the basic resources. The OS, well, that's the master controller of it all. The applications, your web browser, your games, they use those resources to actually solve problems for you. And then there's us, the users, interacting with those applications.
And that right there is the most crucial point to remember. The OS is the great intermediary. It has two main goals. One, make the computer easy for us to use. And two, make sure all that expensive hardware is being used as efficiently as possible. It's both a manager and a facilitator, really.
Okay, so how does a computer go from being just a lifeless box of metal and plastic to a running system that we can actually use? It all starts with the boot process. This is what gives the OS its spark of life. Let's see how that works. So you hit the power button, right? The very first thing that happens is a special program called the Bootstrap program kicks in. Now, this is stored in firmware, something like ROM, which means it doesn't get erased when you turn the power off. Its one and only job is to wake everything up, check on all the system components, and then go find the main event. And what is that main event? It's the kernel. The Bootstrap program's final mission is to find the operating system kernel, load it into memory, and get it running. The kernel is the absolute heart of the OS. It's the one program that is always running, managing everything from that moment on.
All right, so the kernel is up and running, but it doesn't just sit there twiddling its thumbs. It's a super active manager, and it's constantly responding to different events. Its main tools for knowing when something needs its attention are interrupts and system calls.
Now, this is a phrase you absolutely need to remember for the exam. An operating system is interrupt-driven. What's an interrupt? It's just a signal. It could be from hardware or it could be from software, but it's a signal that tells the CPU, hey, stop what you're doing right now and pay attention to me. This is important.
This is multitasking in a nutshell. You see the CPU? It's busy executing a user's program. Then, boom, an I/O device, let's say your hard drive, finishes reading a file and sends an interrupt. The CPU immediately pauses the user's program, goes and handles that interrupt, and then, seamlessly, it resumes the user's program right where it left off. No time is wasted just sitting around waiting.
Okay, so interrupts often come from hardware, right? A system call is a little different. This is how an application program intentionally asks the operating system for help. Think of it as your program politely saying, "Excuse me, Mr. OS, I need to write to a file. Could you handle that for me?" It's a deliberate request for a service. And all of this brings us to a really critical concept for system stability: dual mode operation. You see, to protect the OS from buggy applications, or even malicious ones, the system operates in one of two modes.
When you're just running an app, say your web browser, the system is in user mode. Access here is limited. It's a safe space. But when the OS itself needs to take control, maybe to handle an interrupt or a system call, it switches into kernel mode. And in kernel mode, it has full, unrestricted access to all the hardware. This separation is literally what prevents one bad app from bringing down your whole computer.
So here's how it works. A user program makes a system call, and this triggers something called a trap. The hardware itself flips a special mode bit from 1 for user mode to 0 for kernel mode. The OS then does its thing, executes the request in the safety of kernel mode, and when it's done, it flips that bit right back to 1 and hands control back to the application. It's a really elegant hardware-enforced protection mechanism.
So why all this complexity with interrupts in different modes? Well, it all serves one ultimate goal: efficiency. The OS is constantly juggling different tasks to keep the CPU and all the other resources as busy and productive as possible.
And a key term here is process. You know, a program just sitting on your hard drive, that's just a passive file of instructions. But the moment you double-click and run it, it becomes an active process. A modern OS is running hundreds of these processes at the same time, and it does this by rapidly switching the CPU between them.
Now, to juggle all these processes, the OS has to be an absolute master of memory management. It's constantly keeping track of who is using which chunk of memory, deciding which processes get loaded into memory to run next, and, just as important, cleaning up that memory when they're done. This is absolutely essential for performance and stability.
And you gotta remember, memory isn't just one single thing. It's a whole hierarchy. At the very top, you have these tiny, ridiculously fast CPU registers. And way down at the bottom, you have slow but massive magnetic disks. The key technique here is caching. Copying data that you use a lot from a slow level up to a faster one to speed things up.
I mean, just look at these numbers. They're kind of mind-blowing. Accessing the CPU registers takes less than half a nanosecond. Accessing the disk, 5 million nanoseconds. That incredible difference in speed is exactly why the OS works so hard to manage memory and caching. Keeping the right data in the fastest possible storage layer is the secret to a snappy, responsive system.
Okay, last topic. Let's briefly look at how these core concepts apply when we scale things up, when we're dealing with bigger systems that have more than one processor. You're going to hear these two terms a lot. A multiprocessor system, that's where you have multiple CPUs inside one single computer all sharing the same memory. We call them tightly coupled, and the goal here is to get more work done faster. That's increased throughput. A clustered system, on the other hand, links multiple separate computers together. They are loosely coupled, and the goal is usually high availability. If one computer in the cluster fails, the others can just take over its work.
And that's our review. We've seen how the OS is this incredible manager, using interrupts, dual modes, and super complex scheduling to make our computers useful and efficient. So I'll leave you with this final thought for your exam. Everything an OS does involves some kind of trade-off. What do you think is the most critical one it's always making? Is it raw speed, or is it unbreakable stability? Something to think about. Good luck.